Hey everybody, it's Coach Stoltenberg again, coming to you with the next video in the reactivity unit. This is basically like the second half of the reactivity unit. In the first half, we focused on acid-base chemistry, talking about pH, pOH, learning how to do those calculations, and dealing with neutralization reactions. This is kind of a totally different aspect of the reactivity unit. It's why I call it the second half, because it really has nothing to do with pH and pOH, although neutralization reactions can be redox reactions as well. But the topic for the second half is oxidation reduction reactions. It's just another type of reaction. We're going to learn today how to identify a redox reaction, learn how to assign oxidation numbers, and eventually we'll use that to write redox reactions and split them into two half reactions, an oxidation half and a reduction half. But we'll get to that eventually. Let's start with just introducing it today and learning how to assign oxidation numbers. Alright, so basic definition. Oxidation reduction reactions are chemical reactions in which electrons are transferred. That's the big key here. There has to be a transfer of electrons for it to be considered a redox reaction. It's just another type of reaction to go along with the ones we've already learned, single replacement, double replacement, decomposition, synthesis, combustion reactions, neutralization reactions. Now we're introducing redox reactions. It's just another classification. The interesting thing is a redox reaction can also be classified as one of these other types. Synthesis reactions tend to be redox reactions. Decomposition reactions tend to be redox reactions. Every single combustion reaction that's ever been performed is actually a redox reaction as well. So it's not really 100% something new, because you're going to be seeing reactions that look familiar. You just didn't know that they're also considered redox reactions. Okay, well, how do we distinguish them? How do we know? How can we tell that it's a redox? If it looks like a synthesis reaction, or if it looks like a combustion reaction, how can we distinguish it as also being a redox reaction? Well, that's pretty simple. It comes down to a matter of being able to assign something called oxidation numbers, and if those numbers are changing, then it's a redox reaction. Okay, oxidation numbers. It's a positive or negative number assigned to an atom according to a set of arbitrary rules. We'll look at those rules in here in a second. Good thing about these rules is they're not necessarily new rules. They kind of reflect rules that you should already be familiar with. So this is, generally speaking, one of the easier new aspects, because it actually reflects something you've already learned. Once you've assigned that oxidation number, it's just a matter of seeing if it changes from one side of the reaction to the other, and that's literally all you have to do to recognize whether it's an oxidation reduction reaction or not. If the numbers are all the same on both sides of the reaction, it's not a redox reaction. If the numbers do change, then it is a redox reaction. It's really that simple. Here's the key though. One of those numbers, if it's a redox reaction, from one side of the reaction to the other will go up. Another one of those numbers from one side of the reaction to the other will go down. One is reduction, one is oxidation. We'll talk about that in the next video. But for this to be correct, both things have to happen. You can't have one without the other. You can't have one element whose oxidation number is going up and then nothing else is changing. Just keep that in mind once we get into the actual reactions. If you have something that's increasing but you can't find something that's decreasing, then you need to take a closer look at the numbers you've assigned, because there's a mistake somewhere. So how do we assign those numbers? We just follow a pretty simple set of rules. There is a little variance or some of the rules don't completely cover every single thing, and we'll talk about that. But if you just use what you kind of already know, this is pretty simple. All right, rule number 1, very simple. Free elements are assigned an oxidation state of 0. Free elements. What do I mean by free elements? Talking about elements that are by themselves, elements that are not in chemical compounds with other elements. So if you see any free metals, aluminum, sodium, iron, or any diatomic gases, H2O2, N2, Cl2, these are all considered free elements. They would all get an oxidation number of 0. This is the rule that's probably the simplest rule, but it's the rule that people forget the most often. It's the one I see that people make the most mistakes on. I'm not sure why, it's just something that happens every year. Free elements, no matter what, are always 0. And then as a little side note here, if you see a free element on one side of a reaction, but you don't see that same element free on the other side, which you'll never will, because why else would it be in the reaction, then it's guaranteed to be a redox reaction. Any reaction that contains free elements on one side or the other of a reaction is guaranteed to be a redox reaction, because that means these elements were 0 on one side, and I promise you they're not going to be 0 on the other. Alright, so rule 1, free elements get 0. Okay, rule number 2, oxidation state for any simple one atom ion is equal to its charge. Oxidation state for one atom ions is equal to its charge. So if it's written as an ion, which we don't see this very often, but you will see it every now and again, and you'll definitely see it in some of the practice problems. So this is Na+, this is the sodium ion. Its oxidation number is +1. Beryllium ion has a 2+ charge. Well, guess what its oxidation number is? It's +2. The fluoride ion has a -1 charge, so it also has a -1 oxidation number. So if you're able to determine that what kind of ion it is, then it's pretty simple. That's whatever its charge is, that's its oxidation number. Now this goes for groups of ions as well, but that includes the whole group. So if let's say I have, I get to draw again, I love getting to draw. Let's say I have NO3 negative. This is nitrate, right? This is this polyatomic ion nitrate, NO3 negative. Its oxidation number as a group would be -1. That doesn't mean that this nitrogen and oxygen by themselves are -1. It just means this whole group, 3 oxygens and 1 nitrogen, would have an oxidation number of -1. This is something that is important for you to note and important for you to remember, because it makes assigning oxidation numbers a little easier in the future. Because if you know the charge of a polyatomic ion, you can just count that whole group as a -1, and it sometimes will make things easier in the assigning oxidation numbers for other elements. Also, the other thing about polyatomic ions, their charge never changes, so the total oxidation number for that group also never changes. So anytime you see nitrate, its oxidation number will be -1. Period. It's never going to change. Now, if it's not nitrate, then oxidation numbers are changing. So this only applies to as long as it's the same polyatomic ion on both sides of the reaction. But as long as it's nitrate, it's always -1. Alright, rule number 3. Alkali metals, that includes lithium, sodium, potassium, rubidium, cesium, and francium, will always have an oxidation number of +1. And this is what I was talking about earlier, how these are new rules, but they kind of reflect things we already know. We know that group 1 metals always form +1 ions when forming ionic compounds. They all have that one valence electron that they like to lose, so they all form +1 ions. Well, the rule for assigning oxidation numbers is basically the same. there will always be plus ones. So here we have lithium hydroxide. Lithium would be a plus 1. Here we have sodium sulfate. Sodium would be a plus 1. Very simple. Number 4, fluorine in compounds is always assigned an oxidation state of -1. If you think about it, fluorine is a halogen, group 17. What do you know about group 17s in terms of ions? Yep, that's right. You know that they are always -1. So again, this one shouldn't be that surprising. Notice the rest of the halogens aren't mentioned. Chlorine, bromine, iodine, the rest of them aren't mentioned here because they're not always -1. Chlorine in polyatomic ions, its oxidation number can actually change. But generally speaking, if it's a halogen that's by itself, meaning a halogen that's not in a polyatomic ion, most likely it's going to be a -1. But fluorine is always -1. Chlorine, bromine, iodine, those guys would generally be -1s as well, but they're just not always. So we can't say that for, like, we can't call that a rule for those elements. All right, rule number 5. It's kind of a combination of two rules. It's referencing group 2 and group 13, and just like what we know about them when it comes to ions, about their ionic charge, we see that reflected here as well. Group 2 elements, beryllium, magnesium, calcium, strontium, barium, and radium, as well as zinc and cadmium. These are transition metals. I won't expect you to know those off the top of your head, but I will expect you to know these guys. They're always oxidation number +2. Aluminum and gallium, those are group 13 metals. Yep, you guessed it, always have a +3. So right now, I mean, we're not really learning, like, this is technically new, but it's, like I've said already, it's just reflecting rules we already kind of know. If it's group 2, it's a +2. If it's group 13, it's a +3. So here we have calcium sulfate, that calcium is a +2. Aluminum chloride, that aluminum is a +3. Those rules are set in stone, they never change. Group 2 is +2, group 13 +3. All right, hydrogen. Hydrogen can be a little tricky, but again, it's just exactly how it acts as an ion. We know that hydrogen is unique in that it can act as both a cation and an anion, meaning it can gain electrons and it can lose electrons, which means that is also reflected in oxidation numbers, because whether it's acting as a cation or an anion will determine whether it's going to be a positive 1 or a -1 oxidation number. When it's acting as a cation, as in when hydrogen's in an acid, it's going to have a +1. So here, sulfuric acid, hydrogen's acting as the cation, it's a +1. However, when it's acting as an anion in hydrides, metal hydrides, it's going to be a -1. So lithium hydride here, hydrogen would be a -1. Most of the time when we're doing this, we'll be dealing with positive hydrogens, but every now and again you'll see a hydride get thrown in, so it's a -1. So you have to make sure you're paying attention. Is hydrogen acting as a cation, or is hydrogen acting as an anion? That determines what oxidation number it is. But this is just reflecting its ionic state. So hydrogen's +1 when it's a cation, it's -1 when it's an anion. Oxygen is real simple, and this is exactly what we know about oxygen. Oxygen is always -2. No matter where you see oxygen, hold on, that's the one exception. It's always -2. So oxygen in a polyatomic ion, oxygen just with by itself with a metal, it's always -2. There is one exception, that's peroxide. This is hydrogen peroxide, H2O2. It's actually acting as a -1. I'm not going to give you any examples that peroxide. I'm not going to give you the one exception. So you're pretty much safe in saying oxygen is always -2. All right, and last rule is kind of a big rule because it pretty much takes care of the rest of the periodic table, which there is a lot more, right? We've barely covered any of it. Well, those are the rules we know, and Rule 8 kind of lets us figure out what oxidation numbers are for every other element. Simply saying it's the sum of the oxidation states, So if we take all the oxidation numbers and we add them all up, then it should be equal to the charge on that species. Species is a word that I don't really like using here, but it's the technical definition. It's basically talking about the charge of the compound itself. Whatever the total charge of the compound is, the oxidation numbers of the individual elements within that compound should add up to that. Well, if you think about it, what's the normal charge on any molecule or compound? What does any compound or molecule normally have as far as its charge? Some of y'all may be thinking about it. Some of y'all may have no idea what I'm talking about. It's zero. It's zero. Most compounds, pretty much all compounds, have zero charge. That's kind of why they're in compounds. Makes them stable. So most of the time when we're doing this, those oxidation states, those numbers, should add up to zero. The few exceptions to this would be when we're dealing with polyatomic ions by themselves. Again, that's not something we're going to be dealing with a whole lot, polyatomic ions by themselves. So most of the time what we're talking about is having that charge add up to zero. Those oxidation numbers add up to zero. Alright, well, let's see. Let's get some practice. Practice problems. Alright, lithium. What's its charge? Alright, well, where's lithium? Where can we find lithium? And by the way, if you don't have a periodic table out, you might want to have a periodic table out. Well, I know lithium's group 1, right? And what do we know about group 1? Lithiums are +1. And I bet some of y'all have already written +1 down or feeling really proud about themselves. Well, I'm sorry, but you're wrong. Lithium is group 1. It is +1 when in compound. This lithium, not in a compound. This is a free element. Free elements equal 0. Free elements are 0. Not in a compound, 0. Okay, next one up. Sodium ion. Sodium +1 ion. This goes back to the second rule. Individual ions, their oxidation number is equal to its charge. So this is +1. Oh man, that's just beautiful. Gotta love that. All right, here we go. Number 3. All right, this is our first compound. Well, this one actually contains 2 elements that we have rules for, so this is pretty straightforward. Fluorine is always -1. We have a rule for that. Sodium, now in compound, is group 1, always +1. And look at that. If you have a +1 and a -1, and you put those two things together, what do you get? You get 0. This is what that last rule is talking about. The sum of the oxidation numbers should add up to the charge of the compound. Alright, number 4. Alright, well, we have a rule for hydrogen, right? What's our rule for hydrogen? If it's acting as a cation, it's a +1. If it's acting as an anion, it's a -1. So is hydrogen acting as a cation or anion here? Think about it. Think about it. Alright. Hydrogen's listed first. So it's acting as a cation. So this hydrogen is +1. Yeah, all right. So what does that make this sulfur? Sulfur we don't have a rule for, so this is where rule 8 comes into play. We don't have a specific rule for sulfur, so we have to use that last rule, that rule that says the total sum should add up to whatever the charge is. Well, there's no charge here, so this should add up to 0. So what is sulfur? Think about it, think about it. Alright, I bet at least half of y'all right now are saying -1, because plus 1 minus 1 is equal to 0. And you'd feel really good about that. And you would feel like you're ready to move on to the next one. But you need to slow your brain down sometimes. That quick brain likes to act before the slow thinking brain has a chance to weigh in. Plus 1 minus 1 is 0. But what you have to take into account is that there's 2 hydrogens. So it's not just plus 1, it's plus 2. There's 2 plus 1s. Plus 1 times 2 gives you plus 2. Holy moly. Let me get my eraser out. That was bad. We know this hydrogen is plus 1. Plus 1 times 2 means our total positive is plus 2. Well, what? Plus 2 minus what gives me 0? Yikes. Plus 2 minus what gives me 0? That's right. It's minus 2. So this sulfur is not a -1, it's a -2. Hydrogen is plus 1, we know that. There's a rule for that, but there's 2 hydrogen. So that sulfur can't be -1. That means the total charge of this would be plus 1. And that's not true. So this one has to be -2. Alright, let's look at the last one. I'm going to let you work on this. You can pause it, see if you can figure it out, and then we'll work on it together. So pause it now, see if you can't work it out. Alright. First off, anytime you're assigning oxidation numbers, always assign numbers to elements you have rules for first. We know we have rules for sodium, we have a rule for oxygen, so always do those first. Sodium's group 1, so we know plus 1. Oxygen, not by itself, it's in compound, so we know it's always -2. Alright, so we don't have a rule for sulfur, so we need to make sure we figure it out. But just like with in question number 4, we need to make sure we're accounting for however many elements we have. So I like to do it if I'm just working on this and not 100% sure, I'll just set it up as a really simple math problem down here. We know the total charge of this compound is what? The total charge of the compound is 0. So this math problem, whatever it is, ultimately needs to add up to 0. Well, our positive right here is 1 times 2, so that's plus 2. Alright? And we know we have a -2 from oxygen, but we have 4 of them. So -2 times 4 is -8. Oh, this is going to be fun to draw. Well, that's not bad. Alright, well, we use this to figure out what sulfur has to be. We have a plus 2, a -8. We're missing one number. Well, what plus 2 minus 8 equals 0? Well, 2 minus 8 is what? 2 minus 8 is -6. So this sulfur, for this to be true, has to be plus 6. This sulfur is a positive 6. Sodium's plus 1 because it's always plus 1. Oxygen's -2 because it's always -2. This sulfur is plus 6 based on the fact that these two numbers are what they are, and that there's 2 sodiums and there's 4 oxygens. Plus 1 times 2 gives us 2. Negative 2 times 4 gives us negative 8. So for this to be balanced, for this to add up to 0, this sulfur has to be a plus 6. Plus 2 plus 6 is 8. Minus 8 gives you 0. That's it. That's all you have to do to the sign oxidation numbers is basically simple adding and subtracting, and every now and again some minor multiplication. All you need to really know is those rules and know how to apply them. Alright, well that'll be it for this video. Next video we'll look at the half reactions, learn the difference between the oxidation half and the reduction half, and learn how to write half reactions, which will be lots of fun. So that's it for this one. I will see y'all soon. Bye.